All right, in this video, I want to get some standard traveling salesman problems implemented and get my data collection working well so that I can see what kind of results I'm getting and I can compare it to the literature. And this is really just to give us some solid baselines. I hope to also implement some other baseline methods that are common in this space and really see that my implementation is working as expected. So that way, when we make real improvements, we can measure them properly, right? So I found this Oliver 30 data set, which is referenced in the paper. And then I also found this TSP lib that has a bunch of data sets. Okay. So these are a bunch of layouts that are just from this project, the TSP lib project. And the cool thing about this is they have like the actual optimal solutions figured out. So you can see how well your algorithm is doing. So I think a lot of these have the same sort of format. So if I write some code that parses these files, name type, okay, edge weight section, node coordinate section. Okay, maybe these files are not consistent, but hopefully there's only a handful of different types. So I think if we write some code that parses these things, we will be well on our way. And then the question will be, how do we put that into our graph format, or do we do something different? I think we could probably create a class that does all the graph stuff for us. So we created or extracted out this create graph method before. I think we could probably do better than this. So let's just start implementing some stuff and then we'll refactor it as we go. Okay, so let me pick just one data set and figure out how to parse that file. This is the ant colony system paper from Dorigo. This is where I came up with the Oliver 30. Whoops. I don't know what's going on there. But then as you scroll further down, EIL 50, is that one here? Oh, EIL 51, it's got to be the same thing, right? No. EIL 75. Okay, 76. So for some reason it's adding 1. Let's see. I don't see the 51 here. Interesting. Maybe those are asymmetric. Let's see. And this says symmetric TSP. EIL 75. But then, whoops. but then it has, oh, never mind. It doesn't start on 1. 76. Yeah, I don't know. Unless this is using indexing of 1 and this uses indexing of 0, but then still this count doesn't make sense. So I'm not sure. Okay, these seem to be much larger problems. D198, is that in here? D198, okay. So it seems like there's a lot of overlap, but there are minor differences. A TSP, so this must be asymmetric, I assume. Okay, we'll sort this out later because I really think once we figure out how to parse these files, it'll be not that much work to swap them out. Let's see, KROA 100, this is the last one I'll check. Okay, so here's one. Why don't we start with this? So just to get super scrappy, I'm just going to actually copy paste this. I'm going to create a new folder. Data. And this is KROA 100. KROA 100. Okay, so in this case, we want to find a text string called node coordinates section, and then start parsing after that. And then we have a space delimited. So I'm going to guess that this is the city ID, this is the X coordinate, and this is the Y coordinate. And then we will go until this end of file token. Okay. Parse TSP. I'm just going to accept all this stuff and then tweak it. Okay, so I want to iterate through this file. And basically ignore the data until I hit this key. While lines dot pop 0 dot strip is not equal to this. Okay, so it pops the first line, So it would be something like this. It strips surrounding white space and checks for it to equal that. Oh, whoops. Oh, that's the cool thing about Copilot. I don't think I would have done it that way, but that makes some sense. So that basically has iterated past those lines. Okay, so now we should be at this line, right? So we can throw that away. Okay, I'm gonna get some, whoops. Wow, that's exactly what I wanted. Okay. Node coordinate equals I've also noticed these are integers and not floats. I'm trying to think internally, should I be creating this network X graph? I think the answer is yes, because ultimately I'm going to refactor these into a class, I think, that has this representation under the hood. And then I'll be off to the races with plugging it into my other code. So this might be a distraction, this data class here. I can probably just do this. On the other hand, it's a little bit more explicit. So I think I'm going to keep it. It's perhaps overly complicated, but The other thing I was thinking about is I'm currently storing this position thing, and then it's complicating this function because I'm having to return both the graph and the position, even though I've attached the position to the graph itself. So I think a better way of handling this is just create a function that can extract the position as a dictionary from this graph entity. And then whenever I need position, I can just call that function instead of like continually trying to maintain this as a separate state, even though it's already attached here. So that's another update I plan to do. And that's why I just deleted the POS stuff here as like a separate data structure, because it's already attached as a property of the nodes. Okay, so I think at this point we can return G. Why is it? Oh. I have to update this type annotation. All right, let's test it out. Well, I'll run it from here. From ACO TSP, import parse TSP file. Oh, sorry. Dot model. Okay, G equals parse TSP file data KROA 100.tsp. Okay. Whoops. G.nodes. It starts at 2. That's odd. I must not understand when this is stopping. Okay, while lines is not equal to this. Oh, because it pops it, and then it's comparing the thing that's popped. Okay. So that means it pops this, it sees that it's not equal to that, so it goes to the next. Pops, it keeps happening. It pops this, it sees that it is equal, and then it terminates the while loop and goes to the next line. So we start here. Okay. So Copilot was once again smarter than me. Okay, so now we have 1 to 100. Okay, I think now is a good time to pause and create my graph class and wrap these functions into them. So I'm going to call it a TSPGraph. So maybe I will have a some constructor methods. So I'm thinking I'm basically going to copy paste this. And then okay. So what I just did here is attach this as a class method, which means that I can construct a new instance of this by calling TSPGraph.fromRandom and then use it just as I did before. And now I'm going to add some like helper methods here. So first of all, I can comment all this out. I want to add another class method. Yes. I guess I should complete my type annotation stuff. Oh, interesting. Do you have to put quotes when, I mean, I understand that I'm referencing the same class that I'm defining, but Copilot suggests that I put it in a single quote and now it's not complaining. So I guess that works. Okay. Now my other helper function I wanted to do was this, where I return the position. Let's see. And that will prevent the need for me to like store this in the state and all that stuff. Okay, so now I can comment this out. Didn't like that. Cannot import name TSPGraph from ACO TSP model. Oh, probably because I didn't save it. Okay. So let's try this. G equals TSPGraph dot from TSP file, then ACO TSP slash data KROA 100.tsp. Okay. Here's our position. Okay. I don't really like this is .g. It's okay. Cool, so this works. Now we need to update the rest of our code to use it properly. This isn't used anywhere aside from where I just put it, so I can delete that. So here we pass in a network X graph. I think that's fine. Do we ever use, where do we use this, if anywhere? That doesn't make sense. Oh. .pos is built in to the agent as its position, and I'm using the same attribute name for this position dictionary. But it doesn't look like I use this anywhere in the model. I know I use it in the plotting function, and we'll update that in a minute. But here I'm going to just eliminate that, which means I can eliminate it here. Okay. So I should be able to not touch that stuff. I don't have the create graph method anymore. That's okay. So this is what I need to update. So we call this TSPGraph, right? Or TSPGraph. So graph equals TSPGraph dot from random. Num cities, pheromone init, and seed. So num cities equals num cities, seed equals 1. I'm going to call this TSP graph. And then this is expecting a network X thing, so I can just call .g. Okay. This, oh, okay, and this needs the positions. So I can just call the POS property. So this returns the network X graph, this returns the property of the positions. All right, let's test it. Where am I at here? Oh, I don't even need that anymore. Cannot access local variable graph where it is not associated with the value. Yes, I forgot that I continually modify this graph. I'm thinking, should I have some logic on this graph object? So let me see what this update pheromone method does. I kind of forget. Oh, it's in the same file. So I'm wondering, what if I just take this and make it a method? Okay, I'll need to add this lower in the file, I suppose, or put it in a different file, because this is not yet defined, so I'm going to ignore that just for a second. So wherever I see graph, I can just put self.g. And then I don't need to return because I'm modifying the thing in place. Okay. And nothing about this model is necessarily specific to this model. It just needs to have the schedule and agents attached and so on. So to get around this like import thing, because it's defined lower in the file, I can just say it's an instance of this class, because I'm likely going to have other models as I go anyway. So my type hint can just be this. Okay. I'll delete that in a second. And now this is a method of my TSPGraph object, which does not return graph, right? Okay. Yeah, this is looking much nicer. Now, like I have an object that represents my graph. I have functions that help me load either random graphs that generate positions with random number generators, or I can load established ones from files. And then I have the same interface across, and now there's actual logic in there for updating pheromone trails. We'll see how that evolves, because I can see as we have multiple different rules we want to use for this update, we might want to do something different. Like, for example, maybe we can pass in the details of this logic as a function, and it can just execute whatever function you type in. We'll see. For now, let's just make sure that it works as expected. And I think it does. Awesome. I'm going to shorten this up. Okay, so now let's go ahead and run it on the file here, KROA100. You know, this num cities thing, it would be nice to make it a property of this graph. So I think I'm going to do that. Oh, that's perfect. That's exactly what I wanted to do. It's a little bit redundant if you call this constructor from random, because you have to define it, but that's okay. Now I can call TSPGraph.numCities. Okay, let's delete this. Let's clean up our comments that we don't need. I also want to change the name of this to run episode instead of iteration. Okay. Now let's comment this out. And get it from the file. I want the number of agents to equal the number of cities. Okay, let's see what happens. Oh, I think the labeling starts with 1. Not 0. Where am I calling this? Oh, I see. It's generating a random number between 0 and numCities minus 1. But my data is 0 indexed. So I wonder if I do something like I have the node names as a list, and now but of course I'm passing in the network X graph here, so I don't have access to that method because this is not a network X graph. That property is for the TSP graph. So I guess I can just change this to be a TSP graph. So then that'll just be the index. Do I use the graph for anything else? What did I... Oh. Okay. Now I don't even really need that because that's a property of this. I may as well make that change, or it'll bother me later. Okay. All right, let's see what happens. Where's this coming? Okay. There's no 8? How's there no 8? Oh, I didn't add any edges to this thing. I forgot about that. That should be easy to fix. Oh, and I didn't do the distance. Okay. What I can do here, this method adds a complete graph. It adds edges between all the nodes. And then using those edges, I compute these properties. But I think I'm going to take this as a method of like, enrich graph or whatever we want to call it, that will compute the distance, visibility, pheromone in it, and so on. And then I'll call that same method for this TSP. But first I have to add all the edges. Let's see. Add edges between all nodes to make a complete graph. Whoops. Network X, add edges to make complete graph. I was hoping there'd be like some simple method to add edges between all pairs of nodes. But this double loop over all nodes is probably just fine. Where'd it go? Okay, I'll do this part later. Add edge properties. Okay, so this extracts the positions, computes, whoops. I'm trying to think where to pass this in. I think it makes sense as a initializer. Pheromone, not pheromones. Okay, so this should be the same, right? Distance, visibility, pheromone. Oh, none of this is needed. Okay, so let's talk about what we just did. We had functionality before that added these edge properties, and this thing added edges. Our new method of parsing the file only had nodes with no edges, so we went ahead and added edges between everything except for the self loops. And once these constructors are called, it adds G. We have a pheromone initialization value with a default, and then it calls this add edge properties, which regardless of whether it came from a file or from random, it'll compute all this stuff that we need. Okay, now let's see what happens. Wow, these distances are 23,000. $21,000. Oh, it took 4,000 something iterations. Okay. So we're running it for 100 iterations, and we got to 23,000. Let's go ahead and bump this up to 500. See what we get. $17. I'm going to print one of these edges that actually seems to be a good one to see how the pheromone tracks, because the one I chose from 1 to 8 went to essentially 0. These are obviously much slower, so this 100 city problem is taking a lot longer. Okay, the pheromone strength is still less than 1, but not decaying to 0. So the hyperparameters we're using are probably not very good for this problem given the scale. We were previously around like 20 cities. Okay, this is going to take a while. So while it's running, the last thing I was going to do was get some statistics and start looking at like histograms or plots over time of like the distribution. I don't know. That'll probably take some time, so I might split that into a separate video. Yeah, let's do that. So I'll fast forward so you don't have to sit through this slowly running to show you what the end result is, and then I'll end this video and pick up in the next video to do the rest of the stuff. Okay, so this just completed. The best distance is 22,948, which isn't too far off here. I did find, so in our model we're already collecting things like num steps, best distance, best path, and we can extract that data frame with think it's get model. So let me make this very small just to see what this displays here. I think this is a way to get the data that I wanted. And while this is running, I think there was some like copy paste to clean up. So I want to make sure that the code you see is the same code that gets pushed to GitHub. Okay, so we got I'm confused by this. Oh, I suppose it's not set yet, because we have to go through a certain number of steps, right? 100. Yeah, there's 100 cities, so we don't have any data until... I don't know why it's recording that data for every step then. I might be thinking about steps and runs incorrectly here. Like maybe I should have a full traveling salesman traversal as one quote-unquote step. And then maybe these tools would make a little more sense. But in any case, it seems like right now we're getting what we want. Although, wait a second. Oh yeah, because I get a different model every time. Okay. Yeah, so this data frame basically has a bunch of nonsense, and then the very last row has what I want. And I'm already capturing so really what I should probably do is have something like results. Let's see. Let me make this default dict. So this, every entry will be by default a list. So now I can do something like so I'm going to do something really quick and scrappy and then wrap this up. I don't know. Let's see if this works. Yeah, okay. So now we're getting the global thing here. we see it kind of rapidly improves, and then I'm going to guess that I'll go ahead and run this and then skip ahead in the video so you can see what happens when we do it for a much longer period. Okay, here are the results. We see a pretty steep drop, and really we just care about the minimum over time, right? So like, here's a minimum, then it doesn't beat that until, I don't know, 70 or something. Then it doesn't beat that until 180, and then maybe 320, 350, 400. We get to 21,900. So, okay, so we're at 500 iterations. This is like 10x that. Very interesting. Okay, cool.